Welcome to Statistical Mechanics. This is a series of lectures designed to give you further understanding on statistical mechanics in the chemical context. Through these lectures, you are expected to gain fundamental knowledge on the microscopic properties of molecular systems and its connection to the macroscopic world. This builds on the knowledge that you already have on thermodynamics and looks into the collective behavior of molecular systems. This initial lecture will explain what is statistical mechanics and how it connects the microscopic and macroscopic world. We will also refresh some mathematical concepts on probability that will help us through the development of the module. So let's take a step back. Pause the video and remember what you already know about molecular driving forces and thermodynamics, and how it helped you to answer questions like how things boil, freeze or evaporate, how do oil and water interact, and how do chemical reactions even happen. If you're listening to me again, it means that you have resumed the video after giving some thought to the molecular driving forces that you already know. So let's continue thinking. Many systems in nature are too complex to analyze directly. Solving for the behavior of atoms in a block of ice, the movement of molecules in boiling water, or the interactions of molecules during the diffusion process seems simply infeasible. However, such systems often show simple behavior from a macroscopic point of view. Well, statistical mechanics explains, indeed, the simple behavior of complex systems. Let's look at it in more depth. The world puts on different faces for observers using different scales in the measurement of space and time. The everyday macroscopic world, as perceived on the scale of meters and seconds, looks very different from that of the atomic, microscopic world, which is observed on scales that are smaller by 10 orders of magnitude. The physical laws of the smallest accessible length scales are more fundamental, but they are of little use at larger scales, where we must deal with different physical variables indeed. So each regime of scales has to be described in the terms of variables and laws observable in that regime. For example, atoms and molecules are described in terms of electrons and nuclei without reference to quarks. The subnuclear world enter the equations only implicitly through parameters such as the ratio electron-proton. Similarly, in the macroscopic domain, where atoms are too small to be visible, we describe matter in terms of phenomenological variables such as pressure and temperature. The atomic structure of matter enters the picture implicitly in terms of properties such as density or heat capacity, which can be measured with macroscopic instrument. Statistical mechanics provides a bridge between the microscopic and the macroscopic world. Therefore, statistical mechanics is that branch of physics which studies macroscopic systems from a microscopic or molecular point of view. The goal of statistical mechanics is the understanding and prediction of macroscopic phenomena and the calculation of these macroscopic properties from properties of individual molecules. So how does it relate to thermodynamics? Well, a macroscopic body usually settles down or relaxes to a stationary state after a short time, We call this a state of thermal equilibrium. For instance, we can think of a piece of metal which is perfectly isolated and at a certain temperature. If we put other piece of metal in contact with this one, which is at lower temperature, there is a heat flow during a non-equilibrium stage, and after a relatively short relaxation time, it settles down to another state of thermal equilibrium. Well, thermodynamics is a phenomenological theory of equilibrium states and the transitions among them, while, as we mentioned, statistical mechanics is concerned with deducing the thermodynamics properties of a macroscopic system from its microscopic structure, connecting this way with thermodynamics. Now, when statistical mechanics focuses on equilibrium states, it's usually called statistical thermodynamics. You will see that very often. Well, we are talking that it focuses on equilibrium. Sometimes statistical mechanics can also study non-equilibrium processes. In that case, it's called non-equilibrium statistical mechanics. In this module, we will focus on equilibrium statistical mechanics, as we said, statistical thermodynamics and its connection to thermodynamics, as we have learned that before. So now, before going further into statistical mechanics, let's refresh some of the mathematical concepts that we already learned some time ago about probability and permutations. You already know that, but it is important that we go more in depth into the probability of event A is the number of times that event happens, that we call n sub A, divided by the total number of trials n. Based on that definition, the probability ranges would be between 0 and 1, being 0 the case in which there is no chance and this event will never happen, and 1 that with certain it will always happen. In real-world relativity, probability is always in between 0 and 1. Now, let's go a bit farther into these concepts. What is the probability of rolling a 3, another 3, and a 5 if we are playing dice with a 6-sized die? Let's think about this 3, 3, and 5 combination. The probability of getting a 3 in the first roll is 1/6. The probability of getting 3 in the second row is also 1/6. And the probability of getting a 5 in the third roll has exactly the same probability as the previous two. Therefore, the total probability is the product of the individual probabilities, which is 1 divided by 216. If we formulate the question in a different way, what is the probability of rolling 2 3s and 1 5 in any kind of possible arrangement? That means that we can have this combination, or this combination, or this combination. Well, before we have 3 and 3 and 5, now we have alternative combinations, combination 1, or combination 2, or combination 3. Each of them individually are equivalent to the one we just saw, and therefore we know that the probability is 1 divided by 216. Now, if we can now combine these three, the total probability is the sum of the individual probabilities, and therefore is 1 divided by 72. So with these two things, let's define this mathematical framework. If we have one event A or B to happen, the probability of A or B is the addition of the probabilities of the individual events to happen. If we have the probability of A and B, the probability of A and B is the product of the probabilities. Let's go back now to chemistry. Remember what we learned about gases. We know from our chemical knowledge and common sense that if we opened the valve that connects these two valves, the gas is going to expand to complete the entire volume. So let's look at it from a molecular perspective. Imagine we have 4 particles in these 2 distinguishable bulbs. We call them X and Y. For the 4-0 arrangement, there are 2 possible ways to arrange this. If we look at now at the 3-1 arrangement, 3 molecules on one side, 1 molecule on the other side, there are 4 possible arrangements, which I show here as molecule ABC on the left side, D on the right side, etc. For the 1-3, because the bulbs are distinguishable, we can have these 4 possibilities. So 1-3 is different from 3-1. For the 2-2, we have 6 possible outcomes that I summarized here. So altogether, we have that the total number of permutations is 16 that we can see in this table. So the possibilities to the number of particles we have give us the total number of permutations. Take-home message. So, as we said, statistical mechanics is a bridge in between the microscopic and the macroscopic world, and we have also learned or refreshed about probabilities. What is probability? What happens for the probability? How do we calculate the probability of 2 events, A or B, and also A and B? And the total number of permutations, we calculate them as possibilities to the number of particles we have. This is a take-home message for this first lecture, and we will continue later on further into the